This is clip number 5, topic number 3, EACS 6023, University of Oklahoma. I just wanted to indicate to you and discuss a little bit about a couple of the potential problems with using a correlation coefficient. The first of all is the fact that as we've presented these scatter plots, obviously we've had fairly neat data that tend to follow one general pattern throughout the distribution, either a direct relationship in which an increase with X is associated with an increase in Y, or an inverse relationship in which an increase in X is associated with a decrease in Y, or no relationship at all, which is denoted by a flat line. By the way, no relationship at all would also be denoted on a scatter plot. The scatter plot, the data points might look something like this. In other words, there's just simply a random pattern of data. And that would typically be denoted by some sort of flat line of best fit, and therefore a correlation coefficient somewhere near 0. But there are also a couple of problems that sometimes you'll encounter with data and sometimes you'll encounter with the literature, and that is if the data aren't in fact consistently linear across the entire distribution. And nonlinear data obviously can be a problem for correlation coefficient because something might be calculated that doesn't really adequately describe the data. Let me give you an example. In your PowerPoint presentation, we talk about two types of curvilinear data. There's a curve in the data, either non-monotonically increasing or monotonically increasing. The first, which is monotonically increasing, might be a data set that looks something like this. Through most of the data, there might appear to be some relationship between X and Y. In this case, there's a direct relationship up to a certain point. But then it might start to level off at a certain point. So you might, in effect, for this type of data, and this is a monotonically increasing example. In this case, you have really two lines of best fit. You might get one that looks like that up to a certain point, and then it goes flat. So you have a direct relationship through part of the data, then alternatively no relationship at another part. In economics research, you see that sometimes with marginal utility types of analysis. At some point, efficiency might be increased with adding certain units, but then at a certain point, that marginal utility starts to drop off. So you're not really gaining anything after a certain point, after additional units, additional personnel, or whatever are added. Productivity does not continue to go up, it starts to flatten out. So in this case, you might calculate a correlation coefficient that examines a line of best fit that looks something, if you have all of these data, forget about the green line, the calculation might show something like that. Well, obviously that blue line is not capturing that relationship adequately because the green line better captures it. It's direct and then flat at a certain period of time. There are ways that a researcher has of correcting this kind of nonlinear data problem. One way that one might do it with nonlinear data, if it's monotonically increasing, is using a Spearman rank correlation coefficient. And that's a very simple correction in which the data are actually put into ordinal format, rank ordered, and then the same correlation coefficient is run, so that you can actually get at the relationship without necessarily not being able to examine your data. You're still able to examine the data only with a different kind of calculation. And then there's the more difficult problem of non-monotonically increasing curvilinear data. And again, we'll talk more about this also when we get to regression analysis, because with regression it's also a problem. But this is the type of data in which you might have something like this. You might have a direct relationship through part of the data, and then the relationship starts to actually change direction at some point and becomes an inverse relationship. So you have lines of best fit that look something like this to that point, and then like that from that point out. So obviously this is far more problematic, because if you were to calculate a standard correlation coefficient on this, you might actually get the green line, because these data are pulling the line down, these data are pushing them up. So if you just treat it as linear data, you might get no relationship. Well, obviously, with this type of data, there is a relationship between X and Y. It's a direct relationship to a certain point, then it tends to fall off and become an inverse relationship. So it's important that those relationships are actually captured in the calculation. Unfortunately, for an introductory course, it's very difficult to delve deeply into how to handle that kind of situation, but there are ways in which the data can be analyzed even with this kind of relationship. But I think it's important for you to understand anyway that as you read the literature, researchers should be paying attention to the type of data that they have. One way to do that is simply to eyeball the data with a scatter plot. You can certainly see a relationship like that emerging if you work with that data. It's also important to know previous research because you might actually be dealing with types of data in which other researchers have encountered the same problem. Now, when you talk about costs faced by school districts, there's a definite curvilinear relationship that's been found. The smaller districts tend to face very high costs. The medium to larger districts have very low cost per pupil, and then the extreme urban districts tend to have a little bit higher too. So there's a definite curvilinear tendency to those types of data. And when you're doing those sorts of cost analysis, you need to bear that in mind as you work with your own data, because you kind of could almost expect that to happen with the data that you're working with. So that's another avenue of anticipating and being able to deal with those types of non-conforming data also. And speaking of non-conforming data, on page 19 of your PowerPoint presentation, outliers is always an interesting topic. Obviously, if you have a data set, and outliers, it's an interesting realm of qualitative research, and one in which there's never really a right answer. Obviously, if you have a small data set, like, let's think of an extreme case. Let's say you have n equals 5, and you have something like that. Well, obviously, if you draw a line of best fit through those 5 data points, you have a pretty perfect positive direct relationship between X and Y there. But let's say you're collecting data with 5 data points, and instead of that green dot there, you have a green dot down here. Well, obviously, there are 4 data points that seem to indicate a pattern of relationship, but you have one data point down here that would probably really affect this line of best fit. Our previous line of best fit would look like that, but if we include that outlier, something's going to happen to it. It's going to go down a little bit like that, or maybe even more than that. So obviously that outlier has considerable influence on the type of correlation calculation that is going to result. The problem with outliers is if you're using sample data to predict the population, outliers might have undue influence on how your sample is predicting the population. In other words, it's not that outliers are not important as data points. Any data point is just as important as the other. It's the fact that you're using sample data to predict the population, and if you are unlucky enough in your sample to draw a data point that is so at odds with the rest of the data that it biases your interpretation of the larger population, then you have a statistical problem that's affecting the way that you're interpreting the data, and the fact that and the way in which you're inferring out to the larger population. So outliers are really a problem because if you're using a sample to infer out to a population, outliers can cause undue influence. What to do about outliers? I've done studies before in which I found that outliers are simply a matter of a problem with the data coding. So check that first, check the simple things first. And then what to do about them? Well, I wish there was a magic answer. Obviously, there are tests that you can run on data to ascertain whether a data point is truly an outlier or not. But you really have to make a decision about what to do about the outlier. I've heard some quantitative researchers who are adamant that if it's an outlier, you just don't use it in the analysis. Carte blanche. That's just the way it is. I've been on doctoral committees in which we've argued. I've argued with other committee members about this. Do we have an outlier? Do we just automatically throw it out, or do we take a look at it and see if it's important to retain that outlier in the analysis anyway? And again, there's no proper answer. For a doctoral dissertation, fortunately, you have committee members to kind of bounce that off of. But as a researcher, it's just a matter of experience. It's a matter of using a lot of judgment. Often you'll hear and I've heard this many times before, especially on the part of qualitative researchers, that make the illusion that qualitative research is all about making a lot of decisions, having to structure your research project in such a way that you really have to think everything through because they're all different. But as opposed to quantitative research, in which it's all very straightforward, it's all cut and dried, you take your measures, you run your analysis, and you move on to the next study. It's really not like that at all. Quantitative analysis includes a lot of judgment. It includes a lot of decision making. There are a lot of things that a quantitative researcher might do that another quantitative researcher might disagree with, and no one be right in the absolute sense. You do have to make decisions, but like any kind of research, performing research is a lot of proposing and defending. You have to propose something and then provide a rationale for doing it. So if you do have outliers, make a decision and then have a strong rationale for doing what you did. That's really my best advice for handling that kind of situation. So I wish there was an automatic answer to it, but unlike a lot of elements of research, there isn't one. You just sort of have to use a lot of judgment. You have to be prepared, and you have to provide a rationale for doing what you chose to do. And just one last topic before we conclude the video presentation. On page 20 of your PowerPoint presentation, there's one other statistic that you're going to see reported a lot, and it's a corollary to the coefficient of correlation. You'll see it mostly used in regression analysis, but I wanted to introduce it here during this topic. And that's the coefficient of determination, which is simply the R squared x of y. So simply it's the square of the correlation coefficient, and this is a statistical calculation which indicates the amount of variance in y that's attributable to the amount of variance in x. In other words, there's variance in our outcome variable, there's variance in the y variable. And what we want to know is how much of that variance can we say is attributed to or related to the variance in the x variable. And it's 0 to 100. It has to be positive because it's a square. Even if you have a negative correlation coefficient, a negative times a negative is a positive. So the R squared xy being square will always be positive. And it'll always be a fraction between 0 and 1.0. 1.0 indicating 100%. If you have a coefficient of determination of 1.0, that means you can perfectly predict y based on what you know about x. So it's a perfectly predictable variable. Obviously, if you have a correlation coefficient of 0, you'll also have a coefficient of determination of 0. So let's say you calculate an R sub xy of 0.4, a 0.4 correlation. That means you would square that 0.4, which would be 0.16. So your coefficient of determination would be 16. The interpretation of that is that 16% of the variance in y is related to the variance in x. The remainder of the variance, the other 84% of the variance then is error variance. We really don't know. We really haven't systematically examined it unless we introduce another variable to reduce that 84% variance. That means we have 16% predictability just with the knowledge of our x variable. So that concludes the discussion of correlation. As always, with this or any of the other series of video clips, if you have questions or comments, please use the online discussion board, and we'll certainly, among ourselves, try to address that as best we can. There will also be SPSS demonstrations included as video clips in which we look at SPSS calculations of the correlation coefficient.